Have you ever just stopped and wondered, what are you really made of? We're about to go on a pretty wild journey, one that starts with something you've known about forever, the atom, and takes us all the way to quantum labs orbiting the Earth. We're going right to the edge of what we even know about reality itself. So let's dive in.
So let's start with that big question. What are you made of? I mean, sure, skin and bones and organs, but what are they made of? Molecules, right? And what are molecules made of? The deeper you go, the stranger and more incredible the answers get. And that's exactly what this is all about, that journey inward.
Our story begins where humanities did, really, with this simple but powerful idea, the atom. For thousands of years, this was it. This was the final answer, the fundamental, unchangeable, absolute building block of everything.
And, the name itself tells you the whole story. Way back in the 5th century BCE, a Greek philosopher named Democritus came up with this idea. He figured if you just keep cutting something in half over and over again, you'd eventually hit a point where you couldn't cut it anymore. He called that tiny, indestructible particle atomos, which literally means uncuttable. It was a brilliant idea, just a thought experiment, but it would take, more than 2,000 years for science to actually catch up.
And once science did catch up, that whole uncuttable idea got blown out of the water almost immediately. I mean, look at this. In just over a century, our picture of the atom completely changed again and again. It started as this simple, solid ball. Then it became a plum pudding with little electrons stuck in it. Then, it's actually a tiny solar system with a nucleus. And finally, quantum mechanics comes along and turns the whole thing into this fuzzy cloud of probability. So much for uncuttable.
So yeah, the indivisible atom turned out to be very divisible. And this discovery just ripped open a whole new world inside the atom, a place that physicists sometimes call the particle zoo. It's about to get weird. So how do we make sense of this zoo? Well, we have this thing called the Standard Model. You can think of it as our modern rule book, our best theory for all the fundamental little bits and pieces that make up reality. It's amazing. It explains the forces that hold atoms together, that power the sun, pretty much everything from electricity to light. The only big force that doesn't cover is gravity. That's still a bit of a mystery.
Now, the Standard Model breaks everything down into 3 big families. First up, you've got quarks. These guys build the protons and neutrons deep inside the atom's nucleus. Then you have the leptons. The most famous one, of course, is the electron, which zips around outside the nucleus. And finally, you have the bosons. These are the force carriers, like the photon, which is light, and the super famous Higgs boson, which is the particle that gives everything else its mass. So after all that talk of a particle zoo, here is the absolute knockout punch. Everything you have ever touched or seen or been is made from just 3 of these fundamental particles. That's it, just 3. You take 2 up quarks and a down quark, you get a proton. You take 2 down quarks and an up, you get a neutron. Throw an electron into the mix and boom, you have all the ingredients you need for every single atom in the universe. It's just an incredible simplicity at the very heart of everything.
Okay, I know what you might be thinking. This all sounds great in theory, but how do we actually know any of this is real? If these things are so unbelievably small, how on earth can we be so sure they're even there? I mean, really, how can you see an atom?
Well, the answer came in the 1980s with a totally game-changing invention, the scanning probe microscope. And this wasn't about seeing with light like a normal microscope. No, this was about actually feeling the atomic landscape, one atom at a time. So here's the gist of how a scanning tunneling microscope, or STM, works. You take this incredibly sharp probe, we're talking a tip that is just one single atom wide, and you bring it almost, but not quite, touching a surface. Then you apply a little bit of voltage. And thanks to this bizarre quantum trick called tunneling, a tiny electrical current actually jumps across that gap. As the probe scans across the surface, the little bumps of individual atoms make that current change, and a computer can translate those tiny changes into an unbelievably precise 3D map. Just how precise are we talking? Well, check this out. In 1989, researchers at IBM used one of these things to actually pick up, move, and place 35 individual xenon atoms to spell out IBM. This was a huge moment. For the very first time, we weren't just looking at the atomic world, we were writing in it, we were building with it.
Okay, so we can see atoms, we can move them. And that ability lets us test the fundamental rules that run the universe with just mind-boggling precision. And that brings us to this one single number that seems to be woven into the very fabric of reality itself.
This right here is the fine structure constant. Physicists just call it alpha. It's a pure number, which means it doesn't have any units, like meters or seconds. It's just that number. It's the same everywhere in the universe. And what it does is it basically sets the strength of the electromagnetic force. That's the force that controls how light and matter interact. It is truly one of the most important fundamental numbers in all of physics.
And you really can't overstate how important its exact value is. I mean, our entire existence hangs on it. If alpha were just a tiny, tiny bit different, stars wouldn't be able to fuse heavy elements, like the carbon that makes you up. The chemical bonds that hold molecules together, that make water, that make you, they just wouldn't work. We are balanced on a razor's edge of this exact number. Now, measuring these constants is how we check to see if we really understand reality. But here's the thing about science. Sometimes, when you measure things really carefully, you uncover some deep puzzles. For years, scientists measured the size of the proton using standard methods and got a pretty consistent number. But then, in 2010, a new experiment using something called muonic hydrogen got a different answer, a smaller answer, and their measurement was more precise. This disagreement, the proton radius puzzle, completely baffled physicists for a decade. It just goes to show you, even our most basic particles can still hold some pretty big secrets. So far, we've been talking about discovering the particles that nature already gave us. But what if we could use those rules to create something entirely new, something that doesn't exist anywhere in the natural universe? Meet the Bose-Einstein condensate, or BEC. It's often called the fifth state of matter, and trust me, it is every bit as weird as it sounds. It was predicted by Bose and Einstein way back in the 1920s, but nobody can actually make one until 1995. You create a BEC by cooling a gas of atoms down to just fractions of a degree above absolute zero. And at that point, something incredible happens. The atoms stop acting like individuals. They merge into a single quantum entity, a giant superatom, where all those bizarre quantum rules become visible to the naked eye. So how cold is near absolute zero? Let's put this into perspective. The empty vacuum of deep space is pretty chilly, right? It's about 3 Kelvin. But the lab that recently created a new kind of BEC, they reached temperatures of just 5 nanokelvin. That is 5 billionths of a degree above the absolute coldest anything can possibly get. It is, without a doubt, one of the coldest spots in the entire known universe. Now, making these exotic things on Earth is ridiculously hard, mostly because of one force that's always getting in the way: gravity. So, to push the boundaries even further, scientists decided, well, let's just go somewhere gravity isn't a problem. And this is Beckel. It is literally a quantum physics laboratory that is whipping around the Earth as we speak, bolted to the International Space Station. It's a massive project between NASA and the German Aerospace Center, and it is designed to be the most advanced cold atom lab ever sent to space. So why go to all this incredible trouble? Well, in the microgravity of space, these super fragile BECs aren't getting pulled apart by their own weight. This means scientists can study them for much, much longer. We're talking seconds instead of milliseconds, which is an eternity in this field. It lets them do ultra-precise tests on fundamental physics, like checking if different atoms really do fall at the exact same rate. And they can even trap these atom clouds in weird shapes, like hollow bubbles, that would be totally impossible to make down here on Earth. So think about where we've come. From a philosophical idea about an uncuttable particle, we have now reached a point where we are building labs in orbit to create entirely new states of matter. We've effectively turned the atoms themselves into these exquisitely sensitive tools to measure the universe. So the question isn't just what are we made of anymore? The question now is, what else can we discover with these new tools? The deepest secrets of dark matter, dark energy, maybe even gravity itself, they might just be waiting for us to find them.